Once we have an understanding of the fact that certain things can become electrically charged, it's important to remember that those electric charges can actually move and flow through certain kinds of materials that we call conductors. So when charges flow through a conductor, we say that there is electric current flowing. And if we want to actually measure what we call electric current, well, first of all, we actually use a bit of a strange letter. We use the letter I to represent electric current, just for historical reasons. And what we really mean by the current is how much charge is flowing through the circuit at any given point in time. So in order to calculate that, what we'll literally do is take the charge, Q, which we'll measure in coulombs. We'll take how much charge we see passing a certain point in our circuit for each second that goes by. So we'll track it for a certain amount of time, and then just divide by how much time went by. And so you may see a lot of times this formula using delta t, but just like I've used in a lot of other situations, when I actually use it in the formula, I'm just going to use a regular old t in our calculations. But it's as simple as that. And so current we measure in something called amperes. That's the special name for the unit, which we give the letter A to represent it. But an ampere is really just a coulomb per second, because we're taking charge in coulombs and dividing by time in seconds. So its technical name is amperes, but it's a derived unit that comes from coulombs per second. It's how many coulombs of charge pass a certain point in the circuit for each second that goes by. With that formula in mind then, we can use that to solve some simple problems. So for example, if we wanted to figure out how much charge we would use in running a light bulb, if it requires 15 amps and runs for 6 minutes, we can just solve this using basic given and required information. We're given the current in this case, and that's I. That's 15 amps. Remember, 15 coulombs of charge pass a certain point in the circuit each second that goes by. Time, we're told, is 6 minutes. But just like we've done in a lot of other practices, we're generally not going to use any times in minutes. We need to make sure that it fits with the unit of amps. And amps are coulombs per second. So the time unit that we use has to be seconds for the units to properly fit together. So I'm going to actually multiply this by 60 to see that it's actually 360 seconds of time that's going by. And in the end, I want to find charge. So that's Q. We use the letter Q to represent charge, just like we did in our previous note. So we can start with the formula that we already know, that current is charge divided by how much time the charge is going by for. But in our case, we want to find charge, so we're just going to take the current and multiply by the time that goes by. So we can plug in what we know, and it is 15 amps, but I'm actually going to write its unit just for now as coulombs per second, just to demonstrate to you what's going to happen with the units. And then I multiply by 360 seconds of time that goes by. So when I do that, my 15 coulombs per second has seconds on the bottom of its unit. That gets canceled out when I then multiply by something that has seconds as its unit. And so the only unit that I'm left with in my final answer is that C, it's coulombs. And so I get 5,400 coulombs of charge. And remember, 1 coulomb is just kind of a bucket of charge. It's kind of like a big bucket of electrons. And in this case, I've got 5,400 of those buckets. That's how much charge would be built up if I run this light bulb for 6 full minutes. That's what I've learned. But there are a couple other important details related to current that we need to discuss in this note. And so one of them is just trying to sort out the difference between something that we call conventional current and electron flow. So years ago, back in the 1800s, when they were first experimenting with these concepts and realized that charges could flow and that they could measure these different quantities, they really actually didn't know what kind of charged particle it was that was moving, and whether it was positively charged particles that moved or if it was negatively charged particles that moved. And so they just made the assumption that it must be positively charged particles that were doing the moving, and so they imagined that the current was flowing the way that a positively charged particle would, which means that it would go away from the positive side of a battery and towards the negative side of a battery. because positive charges get pushed away from positive sides of things and get pulled towards the negative sides of things. And that's what we call conventional current. And for many modern engineering applications and many modern electrical applications in general, we still think of things in terms of conventional current. We still assume that it's positively charged particles that are flowing, and so the current travels from the positive side of a battery back around to the negative side. Of course, through more experiments over time, though, they eventually realized that it is not positively charged particles that move at all. The positively charged particles are protons, and they stay locked inside each nuclei. It's the negatively charged electrons that actually do the moving. And so we now know that in reality, current is flowing in the exact opposite direction that they used to think it did. So in reality, current flows away from the negative side of a battery and towards the positive side, because electrons are negative, so they get pushed away from a negative side and towards a positive side. So even though in reality electrons do flow from negative back around to positive, and in some cases we may need to use that fact to solve specific problems, in a lot of everyday applications of electricity, and in the way that most common circuit diagrams are drawn in engineering, we still assume conventional current is actually the way that things are flowing. So it's a little bit confusing, but it's really just that way for historical reasons that we need to try and respect as best we can. Another important concept to talk about is the two main kinds of current. So DC, if you've ever heard of DC, it just stands for direct current. So that just means the current only flows in one direction. It flows all the way around a circuit, but only goes in one direction around that circuit. And alternating current is what AC stands for. And so that's kind of the opposite. It starts by flowing all the way around the circuit in one direction, but then actually, because of the way the electricity is generated, it will switch directions and flow all the way back around in the opposite direction. And so the number of times that it alternates back and forth is actually different depending on if you're in Europe or North America. So most North American outlets, because of the way that we generate our electricity here and pump it into that outlet, the current tends to alternate back and forth about 60 times per second, or what we call 60 hertz. But in Europe, it's more like 50 times per second, just because of the different technologies that they use to actually generate that form of current. We'll talk about these little details in a bit more detail in class, and especially revisit this idea of conventional current versus electron flow, and field any questions you might have at that time.